Okay. What we're going to do today is we're going to focus most of the time on what are called trigonometric identities, and you folks already know a fair number of those, such as the tangent of an angle is what? Tangent of an angle is what? How would you describe that to somebody? Sine of the angle over the cosine of the angle, right? That's called an identity. That's an example. The secant of an angle is the reciprocal of the cosine of the angle, 1 over the cosine of the angle. Those are called identities. Oh, there's a Pythagorean identity I might as well mention. You all know that one. The sine squared of an angle plus the cosine squared of an angle equals 1, always. Okay? So those fundamental identities you've already got in your head, and what we're going to do is learn how to handle ones that are a lot messier looking. So before I start on those identity topics, though, in segment 1, what I want to do is wrap up a few more comments about inverses and maybe take a couple problems out of the book there, because that tends to be a difficult spot for people. And we talked about that in the last session. So I want to wrap up that material. And then, as a way of introducing the identities in segment 2, what I'd like to do is actually take us clear back to arithmetic, because we need to be able to manipulate expressions, whether they're arithmetic expressions or algebraic expressions. And so I want to start with, I want to look at some common type of places people, even at this level and even in calculus, have trouble with arithmetic and algebra. And then we will use the techniques that you've learned in there after this review to then, in segment 3, start actually practicing on verifying identities, and I'll also explain why we want to have this sort of practice. Okay? So, any questions so far? All right. So, the course has covered, up to this point, a bunch of the fundamentals in trigonometry. And so what we want to do is to wrap up a little bit more on the inverses, and here's some connections that we can make based on what we learned in the last session. If we take, and this is the kind of thing I'd like you to keep in your head for the future, for when you move into calculus or into science courses. If you take a sine function through, say I draw one cycle like this where I balance it to the left and right, then what we did in talking about inverses is we know we have to pass the horizontal line test without me repeating the whole story. So what we do is we restrict the domain of that from minus 90 degrees or minus pi over 2 radians to pi over 2 radians. We restrict that domain, and that captures all the possible values of the sine of an angle, doesn't it? From -1 in value up to 1. Okay. On the unit circle, that includes angles that you can see here on your unit circle. And all of those angles have positive values for sine here and negative values for sine here. So you can see all those values from -1 to +1 are captured in angles between minus 90 degrees or pi over 2 negative up to pi over 2 positive or 90 degrees positive. You then form the inverses graph, and it wants to wiggle its way, like this one wants to wiggle its way above and below the x-axis. Over here, when you form the inverse, it wants to wiggle its way up the y-axis. So it looks like, it wants to look like this. And if you look at the restricted domain here, that becomes the range over there. The range over here from minus 90 degrees or minus pi over 2 up to pi over 2 or 90 degrees. A restricted range of values there. Yes?
Does that include negative pi over 2 and pi over 2?
Yes, see, very good question. It does include these endpoints. So the domain you see over here is minus 90 degrees inclusive to 90 degrees, becoming the range over here. Once you get it, it's not hard. But until you do, it's pretty challenging. Just in quick summary now, let's keep on going. If we do this same idea with a cosine, you know looks like this. If we restrict its range to make this 1-to-1, passing a horizontal line test, this is going to go out as far as 180 degrees, starting at 0 degrees. Right? Passing a horizontal line test. And again, that captures all the values from -1 to 1, and it includes the endpoints. You have this in your notes from the previous session. Now, on your unit circle, you can see that that's going to capture angles from 0 degrees, or 0 radians, to 180 degrees, or pi radians. And it's going to be this region. And you can see that captures all of the x values, which you know are your cosine readings, all the positive ones, and all of the negative ones, if your angle was like over in here. The x readings there being your cosine values. Captures the whole family of values from -1 to 1. Taking that to the graph of the inverse, oh, and I forgot to label this up here. This one is the inverse sine of the input. And one more quick comment before I keep on going here is, what did I say inverse functions can be thought of as, always? Angles. You can think of them as an angle. That'll help you because the input then has to be a ratio. Like a half, square root of 3/2. Or other numbers like 0.1, numbers that are between -1 and 1, right? Those things have to be in the domain of values here from -1 to 1, those ratio readings. Similarly, down here on your cosine function, forming its inverse then, it wants to wiggle its way up the y-axis, so it wants to look like this, but it can't look like that and be a function. You have to take the restricted domain over here, and that becomes the range over here, from 0 degrees up to 180 degrees. And the graph is this, capturing values in the domain from -1 to 1, including those endpoints. Any questions? Okay, telling the story over again. I had notes almost like this, I think, in the previous session. Okay, now let's do the tangent while we're at it. If you take your tangent graph, and I should probably label this one here, cosine x versus x, and here now tangent of x versus x. And we know that a tangent graph reminds us of a cubic, except it has these vertical asymptotes at 90 degrees, -90 degrees. And that captures one cycle, doesn't it? Captures one complete cycle. Okay. And it's 1-to-1 already. You can look at these angles and then relate this to your knowledge of the unit circle and see that, again, from -90 degrees to 90 degrees, you will capture all of those values of tangent. And when you're on your unit circle, you think of tangent as your what? Of the terminal side. The slope of the terminal side. Watch out for that. On exam, sometimes people will take something like on the exam, if it's an angle that's sitting like I'm showing here with a marker, and they wrote down a positive answer for the tangent. That can't be right. Because look at that thing. It's got a negative slope. And if you take the y reading divided by x there, the y reading's positive, the x reading's negative, you get a negative ratio. Okay, back to the inverse. So you have a restricted domain of angles here between negative 90 and 90, and then that relates then to the inverse tangents graph over here that is bounded by vertical asymptotes here become horizontal asymptotes over here, up at 90 degrees and down at minus 90 degrees. And the graph looks like this. Okay, now I'm not too concerned in practical words regarding the cotangent and its inverse, although it certainly exists. The two that occasionally do get used that are in the reciprocal functions, those other three functions, are the inverse related to the reciprocal of sine, which you know is cosecant, so its inverse, the inverse cosecant, and then also the inverse of the secant function. Now, you know from your graphing skills that this is slightly different than I presented it last session, is you know that your cosecant graph rides on your sine wave, is the way it's easy to remember. And so if you take this domain right here, just take this portion of it and draw on it, and I hope this red shows up on the recording. Here is your cosecant graph, isn't it? With a restricted domain. If you come over all the way over here now, lay its inverse on there. Lay its inverse on there. It's not too hard to see it. It's right here. And here. So that might be helpful to you. And look at, so there is your inverse cosecant graph. If you look back at the old notes, notice that that red thing is 1-to-1, passes a horizontal line test. Passes a horizontal line test. Okay. And we're not, in this course, we're not going to use that too much, but in second year calculus, you will have forgotten some of your trig by then probably. You can come back and look at the DVDs though, okay? But you will need these kind of things if you move into second year calculus. Now, can't you lay the inverse secant graph down here now? On this one? Yeah, and notice, see this y-intercept here? That's going to become a horizontal asymptote, just like the x-axis up here became a horizontal asymptote. Okay? Because of that 0 right there. And then down here, this y-intercept here becomes a horizontal asymptote location, and you let the inverse secant function ride on that in this fashion, including those points. Including those points. Feel good? Look at the domain of this inverse secant for a second. The domain of the inverse secant. What's it look like? Help me. Domain or inputs. How low can it go on the inputs? Negative infinity off to the left, can't it? Negative infinity. Coming over to, help me. -1, including the -1 on the inputs. And then there's a gap. There's a void, a gap. And then it picks up again over here at 1 and continues on to infinity. this type of thing was showing up in the Math XL homework and test, and some people were having trouble with this kind of an idea. The way the book was expecting you to write it is using set notation, which would say, in this particular case, if you were asked for the domain here, the way the book would expect you to write it in set notation is the set of all x such that x is not equal to values between -1 and 1, right? Not equal to, let's see, how am I going to write that? Actually, the way I'd probably want to write this, x less than or equal to -1, or x greater than and equal to 1 is the way I would write that. Okay. Isn't this much simpler to use interval notation? Okay. All right. Okay. So that captures what I believe you should know in trig for regarding inverses, or their graphs and the restricted domains and associated ranges. All right? Let's look at a couple of things that are problems that like you might find in the book, and then we'll try to wrap this section up. What if you were asked to do this problem? Inverse sine, which means you're going to end up with what result? An angle. You're going to end up with an angle. And let's say inside here I put the sine of 60 degrees. What's the answer? Let's see, is it Mark or David? Jason, sorry. Okay, Jason. The answer is 60 degrees. Do you see the connection between what he just said for that correct answer and what we see back over here on the previous board? Let's come back over here for a second. Where is that particular result? See, you have to work it from the inside out. You start by answering the question, what's the sine of 60 degrees? Right? You're working this from the inside out. So the sine of 60 degrees here is square root of 3 over 2 at 60 degrees. Now the question was, what's the inverse sine of that? So square root of 3 over 2 is right in here before you get to 1, and that's your input to the inverse function. You're putting in square root of 3 over 2 here, that ratio value, and then you're going to come up here and you're going to be imagining what this angle is. Happens to be 60 degrees. Okay. Notice that 60 degrees is in the range of values on the inverse function here, from minus 90 to 90. What if you did the inverse sine of the sine of 120 degrees? Is the answer simply 120 degrees? No, because you have to do this problem first. And so again, what I'm thinking is 120 degrees, and the sine of that is square root of 3 over 2. So this problem translates into inverse sine of square root of 3 over 2. And then you are now on a new function. You're now on this function, and you're going in with that same ratio reading, square root of 3 over 2 again, before you get to 1, and you come back and read the answer right here, and you get 60 degrees also. Okay. Having fun? Everybody can do that? I hope. Okay. Let's play with another one. Let's stick with inverse sine for a second. How about I go inverse sine, and what I have to put in here is a ratio, right? Right, I have to put a ratio in here. So this time, I'm going to put a ratio in. That is going to be the cosine of, how about 30 degrees? Right? Fun. We can mix these things together. I can make millions of these problems. Okay. So what you do is you come in here, you work your way from the inside out, like I keep saying. I'm envisioning 30 degrees, and you can see how critical that first few weeks of trig is. 30 degrees, the cosine is square root of 3 over 2. And we get the inverse sine of square root of 3 over 2. And then we have to be thinking now of that new graph, this thing, square root of 3 over 2. Once again, boy, this is showing up a lot. Answer? 60 degrees. I'll be darned. Yes?
With the inverse in parentheses and not inverse on the outside.
Say that again?
You're doing with the inverse in the parentheses.
Oh, put the inverse inside and put the trig ratio out here? Okay, sure. I'm glad you asked, because that's what I was thinking of doing next. Okay. You're going to love this one. Everybody ready? No. Let's do the tangent of the inverse cosine. And now what do I need to put as my input inside here? A ratio. Thank you. Oh, let's try this. How about 1/3? That's not one of our nice little numbers, is it? Okay. So, we have to work this from the inside out. This inverse cosine in here is an angle, isn't it? That's an angle. So man, when I'm stuck on something, I usually write down, I try to write it in a different way. We know that theta inside there is the inverse cosine of 1/3. Another way of writing this statement is cosine theta, help me, 1/3, isn't it? That's equal to 1/3. Now, back to the artistic side of trig. Draw a picture. Draw a picture where this is your x and this is your r. X is 1, r is 3. X is 1, r is 3. Whoops, r is 3, not y. No, that's not going to be too bad, actually. Isn't that your ratio with theta shown right there? Right? Taking back to the first week of the course, just about. Okay. Now, what's that y value we're reading? No, that's not 2. Oh, come on. What's that y value? Instantly, boom, square root of 8. What?
2 square root of 2.
Square root of 8, isn't it? Hypotenuse squared minus leg squared. Square root of 8, which is 2 radical 2. Okay, now, answer the question. What's the tangent of theta? Everybody wide awake today. Don't tell me y over x. Look at the picture. 2 root 2 over 1, right? It's 2 root 2. So your answer to this problem, the tangent of the inverse cosine of 1/3, you work your way from the inside out, is 2 radical 2. Pretty wild. Okay. But there's nothing in here that you haven't seen repeatedly. You take it back, work your way from the inside out, Start by thinking of that as an angle. Rewrite this in this form, which is more familiar to you. Draw a little picture. Figure out the other leg, missing leg, and then answer the question, what's the tangent of that angle? Let's try one more. One more. Okay. You notice how we started relatively easy, okay? And we got a little fancier as we went. Okay. Let's keep on rolling. See if you can stay with it, okay? Let's say I'm looking for the, probably one like you won't even see in the book. Let's try this. How about the secant of the inverse sine of, and inside here I have to put a ratio. Why don't I call it, how about x over 2? If you can do these and remember this, you're going to be way ahead of calculus students when you start doing things in trig, applications. And keep in mind, it's not just a bunch of math. We're trying to get you so that you can use this as a tool. And as we move through the rest of the course, you're going to see a lot of real practical kinds of things developing. There is nothing different about this problem and the process in solving it than what we just covered right there. Same deal. So you start on the inside by thinking of this as an angle, and think of it as the sine of that angle is this x over 2. Do what next? Help me. Draw a picture. Draw a picture with an angle in it whose sine, think of y over r, is x hypotenuse 2. Excuse me?
1.
What?
X is 1.
Well, x is x. Right. Is that height?
Doesn't have to be 1.
No.
Doesn't have to be 1.
If it was 1, it'd be a half, which would be 30 degrees here. Okay? That's okay. What's this leg right here? What's this leg right here? Which is? I want Pythagorean theorem. Pythagoras figured this out a long time ago. Okay? 4 minus x squared, isn't it? Right? An algebraic expression. Algebraic expression. Okay? Is everybody good with that? You should just be flat out automatic. It's like brushing your teeth in the morning or something. Okay? Just boom. Any questions so far? Everybody got it? Okay, let's come back now to the overarching question. What's the secant of that angle? Well, when you see something like secant, I almost always think of it as the reciprocal of the cosine. In other words, I'm going to take my cosine ratio from my picture here, and I'm going to turn it upside down. As a fraction, I'm going to take its reciprocal, right? And so we know our cosine reading is this radical here divided by the hypotenuse right there, right? This over this is the cosine. And so we want the reciprocal of that cosine. And so this result is 2 over the radical x squared minus 4. So there's the answer to the question without rationalizing the denominator.
4 minus x squared.
Oh, woo. Keeping me awake here, aren't you? Thank you. I saw a bunch of puzzled looks. I was worried. Any questions?
I have a question.
Uh-huh,
It
Stormy?
might be like
Yeah, yeah.
way back, but can't you simplify 4 minus x squared?
No, it's not 2 minus x,
Why am I thinking that?
because lots of people do. Check this out. Everybody remember this. This is a nice little problem that I think you'll love. You all know that's 25, right? Square root of 25, you know, is 5. This is the square root of a sum. Is that equal to 4 plus 3? No. Okay? I would say hell no, but we're recording this. Oh, sorry. Okay. All right. Okay? So don't do that. If you ever see addition or subtraction inside a radical, you're trying to invent new algebra. Don't do that. Okay? Now, if you invent something new, I tell this to students, if you invent something new in mathematics and it's true, you'll become famous. But more often than not, you're going to make a mistake and get something wrong. Okay. So the radical of a sum or difference does not split up into the sum or difference of the radicals. Okay. So that's how you can handle fairly complicated expression. And let me just take a quick peek in the book and see if I missed anything on this material that would be appropriate to cover. Nope, I think I pretty well covered it. Okay, so we'll end this segment now, and then we'll move on to a new topic called identities in just a second here after they get queued up.